Welcome back. We cover in this segment the most celebrated and the most intuitive motion estimation technique, block or region matching. It is used widely, if not exclusively, for video compression, but also for a large number of other applications. We describe the approach and then also look into variations of it, which trade accuracy for speed of implementation. The actual hardware implementation of the technique has also been investigated extensively, since motion estimation is one of the most computationally expensive subsystems in any video encoder. It is indeed interesting that although the approach is so intuitive, block matching actually still continues to be an active research and development topic. If one opens, for example, any journal of video processing, most probably there will be some papers on this topic in it. We will also show some experimental results demonstrating the various approaches towards block matching. So let us proceed with this very important segment. Let us discuss now the block matching motion estimation method. This is probably the most intuitive method out of all the methods we are going to discuss. The steps are indeed conceptually very simple. We see here two different frames from a video sequence, the Foreman video sequence. So this is the frame x of t minus 1 and frame x of t. The two frames can be consecutive or can be further apart in time. We then consider a block in the current frame, the one shown here in cyan. I override it in red. We move this block to all possible positions in the previous frame. We move it, for example, here, or here, or here. And we try to find the best match of the block in the current frame with a block in the previous frame. Let us assume that the best match of the cyan block in the current frame was with the yellow block in the previous frame, based on some matching criterion that we will discuss a bit later. After the two blocks are found that provided the best match, a block from frame t and the yellow block from frame t minus 1, I utilize a vector here to denote the relative displacement between these two blocks, and this is the motion vector associated with this block. Now, this vector can point from block at time t to a block in time t minus 1, as shown here, and in that case it's referred to as a motion compensation vector, and that's how it's handled typically in a video compression scenario. Or it can point from time t minus 1 to time t, and that's what I get if I reverse the direction of the vector. So this might look like a trivial operation, reversing the direction of the vector, but it has implications, since now I'm not looking for a global motion between the two frames, but instead I'm looking for a local motion based on these blocks. And because of that, if I consider all the pixels in one frame, there is not one-to-one mapping between the pixels in the two frames. Also, the way it's depicted here for frame x of t, I divided into blocks, and then I associated one vector for all the pixels inside the block. However, I could associate the motion vector I found just to only one pixel in the block, let's say the pixel in the center. In that case, if I shift the block by one pixel, find another vector, and keep going that way, I am going to end up with a dense field, a motion field that corresponds to each and every pixel in the frame. Let's look what are some of the underlying assumptions in making this approach work out. The first one is that there is no change in the ambient light, which is, of course, the assumption in all of these methods, so that the optical flow corresponds to the motion in the scene. We also assume that the objects are rigid. They don't undergo transformations, like, for example, the lips here of Foreman that are elastic objects, so that a match can be found between the two blocks. We also assume that the objects are translated. They don't undergo any more complicated motions. And then more than that, this translation in the three-dimensional world is on a plane that is parallel to the image plane. So therefore, the objects do not change sizes from one frame to the next. And finally, we assume that no objects appear or disappear from the scene in going from one frame to the next, and therefore a good match can be found. In the discussion so far about block matching methods, we have not addressed the matching criteria one can use, and this is what we would like to do now. We've been using blocks as the units we try to match, but it should be clear that I can use other regularly shaped regions, such as diamonds, for matching, or in general, any arbitrarily shaped regions for matching. And in this case, generally speaking, these block matching methods are also referred to as region matching methods. Now, any similarity or dissimilarity measure between these regions can be used as the matching criterion. So what we see here is a function phi. It's a function of the block at time t and the block at time t minus 1. The block is anchored at n1 and 2, and then I look at pixels around n1 and 2 indicated by m1, m2, which belong to this region indicated by calligraphic n. So xt minus 1 is at the same location, but I'm looking at the displacements d1, d2 that will make these two blocks at t and t minus 1 either similar, in which case I try to maximize this function, or dissimilar, in which case I try to minimize this function. So this function, again, will map the intensity values into an error here, which is a function of the displacements d1, d2. What are some examples of this function phi? I can use a correlation function as a measure of similarity between blocks or regions, and again, in that case, I try to maximize the correlation. Or I can use an error function, such as the mean squared error, or the mean absolute error, or mean absolute difference. In the latter case, the function looks like this, right? So I have again the error, a function of d1, d2, and I'm just looking at the difference between the blocks, and I just take the absolute value of this difference. Clearly, if I use the MAE or MAD criterion, it's simpler from a computational point of view, since I don't need to perform the squaring of the error. The required accuracy of the estimated motion depends on the application. For example, for most of the applications we mentioned earlier, tracking, filtering, interpolation, human-computer interaction, the accuracy of the estimated motion should be as high as possible. If, however, the motion is used for compression, then we can trade accuracy of the motion for computational time. We'll see all these aspects in detail when we talk about video compression. Motion estimation is actually a computationally intensive part of any video encoder. So the first step towards trading accuracy for computations is to restrict the search region in the reference frame. As you recall, block matching consists of taking a block in the current frame and trying to match it to a block in the reference frame. We show the location of this block. So here is the block in the current frame, and let's assume that the center of this block is at location n1 and 2, and we show the location of the block in the reference frame, so the center of this is n1 and 2. So if I consider all possible locations of the blue block in the current frame in the reference frame, shown here in yellow, then we refer to this as exhaustive search. So if the frame says m by n pixels, then I need to perform m times n matching comparisons. In finding the best match of the blue block in the current frame to any of the locations shown in yellow in the reference frame. it is reasonable to assume that the motion of the objects in the scene, as compared to the frame rate, is such that the object can travel only so far. Or in other words, the motion vectors can be arbitrarily so long. So if the video is at 30 frames per second, then within 1/30th of a second, the distance between two frames, the object can travel so many pixels in the scene. We therefore constrain the search within a search region as shown here. The search region is clearly a function of the resolution of the frame. So if the search region is K by L pixels, then the number of matching comparisons is now K by L. And again, depending on the size of the search region, it can result in major computational savings. Even after we restricted the search within the search region, we would like to further reduce the number of computations by not performing comparisons at all possible positions of the search region. So one way to do so is shown here, and we'll show additional ways, examples of additional ways in the slides that follow. So we show here the search region, which is of course in the reference frame, and with one we show the center of the block in the current frame, and this is the point N1 and 2 as indicated in the previous slide. So if we were to consider all locations of the search region, we would need to bring the center of the block of the current frame that we try to match at all these vertices and find a matching criteria, based on a matching criteria, find a matching metric, and we can assume for the time being that we use an error criterion. Instead of doing this, we first consider the grid location numbered 1 here. So the center of the block again of the current frame will be brought here at 1, and this error will be evaluated. After that, I will consider the 8 neighbors of 1, also numbered 1 and shown here in blue, and I will evaluate the error at these 8 additional locations. And let us assume that the minimum of the error was found at the location here indicated in red. After that, I'll consider the 8 neighbors of the pixel numbered 1 where the minimum was found. So I'll consider the 8 neighbors numbered 2. And let us assume that the minimum was found at this location, at which point I'll repeat the step. I'll consider the 8 neighbors of 2, which are numbered 3. I'll look for the minimum, assume the minimum was at this location, and therefore the motion vector associated with the block centered at N1 and 2 in the current frame is the one shown here. Let us see now why this search is called logarithmic search. So let's denote here the axis like this. And let's assume that the size of the search region is from this point here, minus P0 to P0, and from 0 minus P to 0P. So the search region has size 2P plus 1 by 2P plus 1. And then let's denote by K the log of P, log base 2, and let's take the ceiling here. So for this specific example I show here, P equals 7, therefore this is a 15 by 15 pixel search region, and also K equals 3. So if we follow here the steps that were shown, the first pixels we considered were at this distance D1, and D1 is equal to 2K minus 1. So it's K equals 3, so this is 4 pixels D1, right? So following the steps that I described, the distance here after the first minimum was found, let's say this is d2. d2 is d1 over 2, therefore is 2k minus 2. This distance here is d3, and d3 is d2 over 2, therefore is 2k minus 1. And we stop at the point where the distance is equal to 1 pixel. Therefore, we take k steps in this process, and since k is the logarithm of p, where p again is half the dimension of the search region, this is called the logarithmic search. The 2D logarithmic search we just described is meaningful, since at each step we are looking at the direction of reducing the error, so we are descending on the error function. The steps we take in these descending directions are halved at each step. So it's indeed a smart way to visit the pixel locations in the search region, and if the error function were convex, then we would obtain the global minimum within the search region. So we show here the matching error as a one-dimensional function of the displacement. And we depict here a convex function. It has a global minimum at this point, and again this 2D logarithmic search would attain this point shown here. In practice, of course, we have no idea of how this matching error function would look like, and most probably it's a non-convex function. And here's an example of a non-convex error function, matching error function, and in that case clearly we may get stuck in one of the local minima, and therefore we won't get the best possible solution, the smallest matching error within the search region. Another way to reduce computations is, instead of using all the pixels inside the block to find the error, be it the mean squared error or the mean absolute error, we only use 1/4, 25% of the pixels at each comparison. So here, for example, you see an 8x8 block we try to match, and in one location the red pixels numbered 1 are used, in the next location the blue pixels numbered 2 are used, and so on. Again, this method intuitively makes sense, but one can always come up with examples for which this method will fail to obtain the global minimum. And this method can be used with a search region or without a search region, so in other words, when a global search is performed. And yet, as a final example of a method for reducing computations is shown here, again for an 8x8 block we would like to match. Instead of using all 64 pixel values in the evaluation of the matching error, the projections of the rows, as shown here, so the sum of the intensity values in each row, as well as the projection of the columns, the sum of the values along a column, are used. So in this particular example, instead of comparing 64 numbers for finding the error, we compare only 60 numbers, and clearly there's a major reduction in computations. So we saw with the previous techniques that one can use fewer search locations and or fewer pixels in computing the matching error. A scheme that combines these two features is referred to as the hierarchical search method. So we make several low-resolution versions of both the current and reference frames, as shown here. The frame is first low-pass filtered, then downsampled by a factor of 2. We continue with another low-pass filtering, another downsampling by 2, and we can keep going this way. So here we see a 3-level representation of the image. So we start performing motion estimation at this lower level using any of the techniques that we have covered so far. Since the resolution at this level is considerably reduced, we could perform global search, for example, in order to obtain an accurate estimate. The estimated vector is here multiplied by 2 in each direction, in the x and y direction, and it is refined at this higher level. The estimated vector is multiplied by 2 again and serves as the initial condition for the estimation at the highest level here in this 3-level, again, representation of the frame, and then from this highest level the motion vector, the final motion vector is produced. This approach is being used quite often since it provides improved motion estimation results. It might suffer from the elimination of small objects due to the downsampling. On the other hand, the low-pass filtering provides some immunity to noise. Conceptually also, the low-pass filtering filters not only the intensities but the DFT, the displaced frame difference, or the error based on the compensation, so that the error function is possibly convexified at the lower levels, and therefore a global minimum can be found at this lower level even with one of the fast methods. It should be clear by now that the block matching methods we described in the previous slides provide pixel or PEL accurate motion vectors. So here's an example of such a vector, and this means that both the tail of the vector and the head of the vector are located on the locations of the grid points. Very often we are interested in motion vectors with sub-pixel accuracy. For example, in compression, sub-PEL motion estimation is providing sizable compression improvements over full PEL motion estimation. So a way to obtain half-PEL accurate motion vectors is shown here. After the best vector at full resolution is found, as shown again here by this example, this vector, we consider the 8 neighbors of this pixel here at half-PEL resolution. So these x's here are locations for which the intensity value of the image is not known. The intensity value is known only at these square locations, and therefore in performing now block matching at these half-PEL locations, the intensity values of the image, of the two images, both at the reference and the current frame, need to be interpolated. And one can use bilinear interpolation or any interpolating kernel to find these non-existing values. So after interpolation, if the minimum is found at this point, then this is now the half-PEL accurate motion vector. Clearly, one can continue with this process to obtain quarter-PEL accurate motion vectors, 1/8 PEL accurate motion vectors, and so on. It's also mentioned here that the optical flow techniques that will be presented next provide real estimates of the motion vectors, so real accuracy, non-integer values, since they're the result of solving a set of linear equations. We show here an experimental comparison of some of the block matching techniques we discussed so far. The reference and current frames are shown first, both of which are 720 by 480 pixels. We then show the displaced frame difference, which can be thought of as the motion compensation error when the motion vectors are equal to 0. It's noted here that in the frame difference, the dynamic range of the image doubles. So the intensity in the original frames ranges from 0 to 255, since 8 bits per pixels are used, and the intensities in the frame difference range from -255 to +255. In what is shown here, they have been mapped linearly into the 0 to 255 range. So -255 is represented by black, like for example here. 0 is represented by gray value, and +255 by white. It is clear from this image that there is energy, there are non-zero values where the objects are moving. These are temporal edges. So the ball is moving, for example. The arms and hands of the player are moving. There is, however, non-zero energy non-zero values also when it comes to stationary objects, such as the table here. You see that the edge of the table here is non-gray, is non-zero values, as well as the calendar on the wall. And this is because there is a panning motion of the camera with respect to the scene. So there is global as well as local motion in this particular scene. Using a block matching algorithm with 16 by 16 blocks and full search, we obtain the results shown here. We see that most values are equal to 0, grade values, as expected. This is, by the way, the best result we can obtain under the specific motion model we are using. We see, however, that not all values are 0, especially around the moving arms and hands of the player. So full search should have given us a 0 compensation or prediction error. However, the results are as good as the motion model we are using. A main component in this motion model is that all the pixels in the block are undergoing the same motion. And this modeling assumption is clearly violated at motion boundaries. Maybe, for example, here, where part of the block belongs to a moving object, while the other part of the block belongs to the stationary background. We see the result next, the displaced frame difference, when logarithmic search is used. The displaced frame difference is now greater, as expected, since we have traded computational speed for accuracy. Finally, we show the result of the 3-level hierarchical search. The displaced frame difference is now almost as good as full search, and better than the result we obtained with logarithmic search. Apparently, the low-pass filtering that is performed has beneficial effects, as already mentioned. If the motion estimation is performed for tracking applications or filtering applications, then full search under this model should be the search or the approach of choice. If, however, we are performing motion estimation compensation for video compression applications, then we can afford trading accuracy of the motion for speed of implementation, and in that case, because in that case we'll have to send the displaced frame difference shown here, as will become clear when we cover video compression. So the other approaches, such as the logarithmic search or the 3-level hierarchical search, are definitely some of the choices one might exercise. In different parts of the course, we will be making use of the software package named VC Demo. With this, we'll be able to explore the possibilities of compression for both still images and videos. The package can be downloaded at this URL here, and it is the result of the work at the Information and Communication Theory Group at Delft University of Technology in the Netherlands. You see here a snapshot of the user interface. VC Demo is completely menu-driven, so no programming experience is necessary. Through the user interface, the user can control the various parameters that will control the various compression schemes that we will be studying. So again, we'll be making use throughout the course of this package, and right now we would like to use it to demonstrate the results of block-based matching motion estimation. Let us now use VC Demo to demonstrate block matching based motion estimation. So after we start the software, we can go here to open an image sequence. We see quite a few YUV sequences. Let's say we pick this one. So here we see the first frame of the sequence. Here we have a video player module. So if I press play, we see all 21 frames of this video sequence. Each frame has a resolution 288 by 352, and again there are 21 frames in the sequence. So going here, we can invoke the motion estimation module, and then this interface comes up. We have quite a few choices. The first is whether we're going to use hierarchical motion estimation or not. So either we pick original resolution only, or a 2-level or 3-level hierarchical. We then have a choice of the search method. We can do full search or one-time or n-step logarithmic search. We have a choice of the block size. It can be 2 by 2 all the way to 16 by 16. Let's say we pick 8 by 8. Then we choose the size of the search region. So it's 15 by 15. That's the maximum displacement that we will allow. And finally, we can step through the motion estimation frame by frame, or we can let the system run on its own. So if we press apply, we see here 4 in total windows. So the upper right one shows us the frame difference. The bottom left shows us the vector field on each 8 by 8 block, and the bottom right shows us the displaced frame difference. Again, gray represents 0, black minus 255, white plus 255. Clearly, the motion compensated frame difference, bottom right, is closer to 0 than the frame difference. And actually, this also can be seen here by the statistics on the right. You see the frame number and then the variance of the original frame, the frame difference, and the motion compensated frame difference. So by and large, the variance decreases when I look at the frame difference, and it further decreases when I look at the motion compensated frame difference. This is the prediction error. This is the whole idea behind prediction error, that the variance decreases. The last column shows the entropy of the vector field. We'll spend quite some time talking about these issues, and by and large, the entropy is proportional to the number of bits I will need to represent the vector field. So I can press here show again and see this short video repeating and demonstrating the effect. By the way, it should be clear here that I have both global motion as well as local motion due to the motion of the car, and this is reflected by the motion vectors. Ideally, it should be a very smooth motion field, but due to the reasons that the model breaks down, we see that it is probably not as smooth as it would be desired. So this hopefully demonstrates to all of you these ideas we've been just explaining here in different words and different ways. And of course, you are encouraged to just download this package and experiment at your own time, at your own leisure, and just pay attention to all the various aspects we detailed here.